Welcome to Calc 3. This is line integrals over vector fields examples, section 14.3. So let's suppose that we have the line integral over the vector field f for f equals x times y, comma x on the curve y equals x cubed from x equals -1 to 1. So we can parameterize this function and we can say that r equals t comma t cubed, where t is an element of -1 to 1. This is a nice easy parameterization. We can check that it's conservative. It's a nice easy way to check real fast. So if we do nx minus my, we get 1 minus x. So this is not conservative. It's not equal to 0. So we can't use the fundamental theorem of line integrals. So we have to go back to our original definition that over the line integral over the vector field f is equal to a to b, integral of a to b of the field evaluated at r, dot the derivative of r of t dt. So this becomes the integral from 0 to 1 of t to the 4th, comma t, when we input in our t and our t cubed, comma t, dotted with our derivative, which is 1 comma 3t squared dt, which gives us the integral from 0 to 1 of t to the 4th plus 3t cubed dt. This is a nice easy integral to solve. 1/5 t to the 4th, t to the 5th plus 3/4 t to the 4th, evaluated from, not from 0 to 1, from -1 to 1. Response should be -1 to 1. So we get 1/5 plus 3/4 minus -1/5 plus 3/4. So we get 2/5 as our answer here. So let's look at another problem here. So let's find the line integral over the vector field f along the curve C. For the vector field f equals 2x, 2y, 2z, for r equals cosine of t, sine of t, sine of 2t on the interval 0 to 2 pi. So we could do this from 0f dot dr. We could easily evaluate this as from 0 to 2 pi of 2 cosine of t, 2 sine of t, 2 sine of 2t, dotted with negative sine of t, cosine of t, 2 cosine of 2t, dt. This is using the definition of the vector line integral over the vector field along the curve C. However, we could check conservative for vector fields, because the line integral above is not a hard integral to solve. We will just have to do a couple of u substitutions, and that's, maybe takes more time than what we'd like to do. So if we check conservative, so our curl of f, this is a three-dimensional vector field. So we can check our curl with our cross product here. So we have our I, our j, and our k notation here. Partial, partial x, partial, partial y, partial, partial z. We have 2x, 2y, 2z. And so we get this as the vector 0, 0, 0. So this is a conservative vector, so we can use the fundamental theorem of line integrals. So our point A is equal to the curve evaluated at time equals 0, which is cosine of 0 is 1, sine of 0 is 0, sine of 2 times 0 is 0. And B is the curve evaluated at 2 pi, which cosine of 2 pi is 1, sine of 2 pi is 0. And sine of 4 pi is also 0. So again, we start and we stop at the same place. So since we're starting at stopping at the same place, we know that for a potential function phi, phi of b minus phi of a equals 0, since we start and stop at the same place. So we don't actually need to calculate phi, because we know that regardless of what phi we're evaluating, we will start and stop at the same place, and so we don't actually need to calculate our phi. But our phi we could calculate for practice. If we were calculating our phi, so phi sub x equals 2x, phi sub y equals 2y, phi sub z equals 2z. So this means that phi has to equal x squared plus y squared plus z squared plus some constant. So again, if I substitute in my a and my b, I do the subtraction, I get 0. So as always, if you have questions, please let me know.